Okay, we're going to take everything that we've talked about so far and put it all together and try to determine now whether a whole molecule, not just the bonds within it, but whether the whole molecule is polar or whether it's not polar. A polar molecule has to have two things in order to be classified as polar. First of all, it has to have polar bonds involved with it. So if you remember, a polar bond means that the electrons are not shared equally and one of the atoms has possession or has control of those electrons more of the time than the other atom that it is sharing the electrons with. So an unequal sharing of electrons in the bond. And then the second thing it has to have, if you're going to have a polar molecule, is that it has to have, the way I like to describe it is a partially positive end and a partially negative end. So you have to think of the shape of it in 3 dimensions and look for some of the symmetry that's involved there. So let's start with a real simple molecule, a Cl2 molecule. Again, a lot of these that you'll see on here, we've already drawn dot structures for. We've already determined the shape of them, so now we're going to look at them and try to determine if the molecule itself is going to be polar. So this Cl molecule, when we talked about polar bonds, we said, well, these are both Cl molecules, or Cl atoms, and so they're going to be pulling equally, and so what that means is that this bond isn't polar. So it doesn't fit the first requirement of having a polar molecule because it doesn't have a polar bond. So if it doesn't have a polar bond, it can't be a polar molecule. So this molecule is going to be non-polar, or you will also see your book call this purely covalent. And these two terms can be used interchangeably. You can call it non-polar, you can call it purely covalent. So purely covalent just meaning it shares everything exactly equally. There's no unequal sharing. So it's a pure covalent bond because nobody's being greedy there. Now, on the other hand, if I look at an HBr molecule, if you compare the electronegativities of these two, you'll find that the Br, the bromine, wants the electron a whole lot more than the hydrogen does. And so it's going to pull harder. And so this end's going to be partially negative, while this end is going to be partially positive. So it does have a polar bond, and because there's only 2 atoms involved in here, this end is partially negative, this end is partially positive. So this molecule will be classified as polar or polar covalent. Okay? If I look at a carbon dioxide molecule, this one is also linear, just like these two were linear. I mean, this is linear because it only has 2 atoms in it. But this is linear because your central molecule, or your central atom, has 2 groups around it. So it is a linear molecule. Does it have polar bonds? Yes, because this isn't going to pull evenly. An oxygen is more electronegative than a carbon, and so this is going to have the electrons more of the time. So this is partially negative, this is partially positive, this is partially negative. But if you remember, these guys are 180 degrees apart. It makes a nice straight line, and so I can't say that I have a negative end and a positive end because the negative is on the outside and the middle is on the inside. So it's not like you can turn it and say, this side's positive and this side is negative. So I can't do that to this molecule. So even though this molecule has polar bonds, it doesn't have a positive and negative side to it. So this molecule is classified as non-polar, or again, as the author of your book puts it, purely covalent. Both terms are equivalent to each other. Okay? Now let's look at this one. Again, I have partial positive and partial negative bonds in here. So just like up here, this would be partially negative, this would be partially positive. But if I look at this molecule, these bonds over here will also be polar. But if I look at this, this whole molecule is very non-symmetrical. I've got oxygen on one side, I've got hydrogens on the other side, and since I already know the bonds are not polar and this molecule is not symmetrical, then this molecule is going to be polar as well. Okay? Now we're going to start looking at these ones that had 4 groups around them. This one, again, we've got some partially negative and partially positive pulling of this, but it's sort of like this one over here where all of the hydrogens are going to be partially positive, the carbon's going to be partially negative, but when you do that, the carbon's smack in the middle, and if you did what I asked and you watched the video where the gentleman had all of the really nice models, what you see is that that carbon's in the middle, and you've got hydrogen here, hydrogen here, hydrogen here, hydrogen here, and so it's almost like this ball, kind of, where you've got all the hydrogens surrounding the carbon, so I can't orient that molecule so that one end of it's different than the other end. It's a very symmetrical molecule, so even though the bonds are polar, I don't have sides of the molecule. So this molecule also will be nonpolar. Now when I get down here, everything is not as symmetrical anymore. I will have polar bonds because these guys they're not the same atom. And so for example, a carbon and a chlorine, this will have a negative end and this will have a positive end to it. The hydrogens are going to be polar bonds as well because they're not going to share equally with this carbon. But unlike this one, this top atom is different, and its electronegativity is not the same as that of hydrogen, so therefore this molecule isn't symmetrical. It doesn't pull one direction or the other direction, so this molecule also will be polar. The ammonia molecule that we've looked at several times, even though it's symmetrical on the bottom, you have this lone electron pair up here. We talked about how greedy it was for space and how it kind of shoves the hydrogens down. And so regardless of whether these bonds are polar or not, and they are because the nitrogen and hydrogen don't have the same electronegativity, this lone pair, because it's a lone pair of electrons and it's got some negative charge on it, it's like this is on one end of the molecule and then the hydrogen's on the other side, so the molecule isn't symmetrical. And so this is going to be a polar molecule as well. The water molecule, again, very similar to that. The oxygen is going to pull more of the electrons than the hydrogen, so this is partially negative. These are partially positive. So I can say, well, this side of my molecule is positive, this side of my molecule is negative. It's got a bent structure to it. So since here I've got a positive side and a negative side, this molecule also will be classified as polar. So when you look at these, again, you're looking for two things. You're looking, first of all, that they have polar bonds. And most molecules, a lot of them are going to have polar bonds unless you've got two identical atoms that are sharing the electrons together. So while almost all of these molecules have polar bonds, they don't all have a positive or negative end of the molecule. They're not all super symmetrical. You know, this is symmetrical because the carbon's surrounded by 4 hydrogens. This one is symmetrical because there's equal pull on both sides of this carbon. But the rest of them don't have that same symmetry and they don't have equal pull of the electrons, so therefore it makes these other molecules polar. Now you may be asking, why is all this even important? And so in the last section of the chapter you will read about why that is important, because it has an awful lot to do with whether some of these compounds will dissolve in water or whether they will not. And so that's the whole key. That's where all of this is going. That's where it's all culminating, because what we want to know is if I want to be able to dissolve this in water, am I going to be able to or not? And so that's where the whole discussion is going, and you'll read about that in the very last section.